And it really comes down to, little or no manual server management. There's always going to be some level of management when we deploy applications, right? Automatic elastic scale, built-in resilience, because if it's a serverless thing, it should just be there. And if I have to actually engage with the thing to make sure that it's actually fault tolerant, that's an issue, right? It has to be always available and it has to be instant. And I think this last bullet is probably the one that I think is changing the minds of a lot of people around serverless, and really coming down to changing the way that we use and buy software as developers, and the way we actually run these things. I love the concepts of consumption-based billing. What is my monthly bill? I don't want to deal with buying a license for something for a year. I only use it for like 2 months out of that year. It's wasted compute, especially in the day and age of us having these large bills to the large cloud providers. How do we actually minimize and become very efficient with our compute, and only have like kind of consumption-based rating and billing for around these things? And I think if I think about those 4 kind of core principles of serverless, that's pretty cool. And I think we've come a long way with serverless. Serverless, we have these compute platforms, Fargate, Azure services. I really love Google Cloud Run. I think it's pretty cool. You can, take any containerized app and just throw it at Google Cloud Run, and it'll scale that thing up and down. It's pretty slick, y'all. I'd go check it out. But it's kind of just managing the infrastructure underneath. And then there's this emerging group of companies that are doing, serverless functions. Again, the big 3 all offer that. But then, I think about, Cloudflare Workers and Netlify and these sort of things. I'd love Netlify. I think Netlify is super cool, where it's more event driven. It's a function that a developer can call, and it just basically spins up, spins down, is used as needed. It's just a function that basically, as you code, just sits in a directory. And I think these serverless functions are pretty cool. And I loved the concept of serverless functions and the concept of lots of things that we do. And then there's these larger serverless app development kind of platforms that are starting to emerge, where I think they're putting it all together. They're getting compute, the functions, the whole thing. And I think, we start thinking of like the modern IDE, and what is that going to look like? Do we get to the point where, we're kind of doing some of these things? I do believe that this kind of next generation of app development is happening. And it's really because I think some of the things that we've seen over the past 2 years of building serverless and using this, and the value it can provide to people who use these things. Now, when you start to deal with data, things get a little bit more complex when you within a serverless environment or without, right? Like when you start to deal with data, you have to start thinking about, great, I'm resilient and I'm fault tolerant, but to what level? What's my failure domain? Is my failure domain a region? Is it just an AZ? Is it an entire Kubernetes cluster? How do I survive the failure? Because these things do go down, right? How do we scale these things so that they can actually, if it's serverless, well, I don't want to be serverless within a single region. I mean, how do I expand beyond regions, And for databases, the transactional guarantees get really tricky here, because if I have, a person in New York writing a record and somebody in Sydney writing the record at the same time, who wins? How do you deal with these kind of conflicts? And so there's things you have to do in the software to actually mitigate these sort of things. But if you take this and you take those serverless principles, and now let's apply it to, the database. And then that's what we're going to use as our example here. Well, in a database in the old world, we sharded database, we had, 2 instances of a database, multiple shards. So we got scale. We were doing the synchronization between 2 sites. Maybe there's a primary and a secondary, one in one region, another in secondary region, or maybe I need coverage in Europe. So I have, this sharded full database thing going on in US West. And then I got something over in Europe, and I'm doing synchronization, and it gets really complex. In this modern world, this becomes more of a distributed platform, right? And we start to apply these principles to this distributed mindset, so that each entity is kind of part of a bigger whole. And that's how you get serverless, because scaling big, massive pieces up and down to zero, it's near impossible to do that. It takes 10 people or even 2 people to do that. That's too much. Serverless is about automation. It really is, and it's how do you automate these things? And so when we think about the concepts or the core primitives of our application, how do we break them down so that we can scale them separately? And that's really the trick behind serverless. Now, in a serverless database, again, the data creates big challenges. How do we auto scale? putting data close to users so they have low latency access to that, and thinking about these transactional latencies, right? Ultimately, I feel like serverless in the term should be infrastructureless, because these are the things get really complicated. Scaling across regions, these sort of things are really tricky. I think ultimately the end game of serverless is about, it's the value to the user, whoever is using these sort of things. And for developers, I think it's about starting instantly. It's about eliminating the need to manage, upgrade, operate, no operations, right? I don't want to deal with scale, and I want to completely eliminate downtime. I don't think there's a developer in the world who wants to even think about any of those things on the top of this slide. I think what we want to do is just build. I think we want transactionals. We want data to be guaranteed consistent. We want it in real time. And I think ultimately the end game of this, at least for us at Cockroach Labs, when we think about a serverless database, if we really think about that, and you just have an API against that database with endpoints around the planet, could the database be something simple as a SQL API in the cloud? I don't even have to think about any of these things. And if we remove the stuff across the top of the slide and we start to just build and code against the database just as an API, things get really interesting. And I think that's to me, that's the ultimate vision of kind of what serverless can do for the database. And so, think about that. What could that mean for you and your application, where you're just some blank API in the cloud, right? And that's, for us, it's a SQL API in the cloud. Now, I'm going to actually give a little quick demo here. Why not? I mean, I'll go out on a limb here. So I'm going to go to cockroachlabs.com, and you could spin up a cluster using our serverless instance right now. I just need to log in. I just hit the sign. Oh, I'm already signed in. And so it's really as simple as create a cluster. We have serverless or dedicated. Dedicated is full instances where we have SREs managing it. It's private. Our serverless instance is multi-tenant. You choose a cloud provider, choose a region. Right now we're AWS and Google Cloud, and you set a spend limit. Now this comes back to the consumption-based billing, and as consumption-based billing becomes kind of more important, understanding consumer behavior around it is actually pretty important. We've gone a long way to think through this. And for us, it was like, well, let's just put limits in place so that, you're never going to spend more than $10 a month if I put $10 in my spend limit, or zero. It could be completely free forever. And for us, that means, well, I have to throttle usage of the database over time. What does that mean for your application? Because I don't think anybody really likes to get a bill at the end of the month where some service just ran wildly for, 20 days and I get charged, thousands of dollars, right? And so I think as we build these things, we as developers need to be cognizant and aware of what people really want. And for us, having spend limits was a big deal. And then we just named the cluster. So I could just create a cluster. It's going to be ready in a couple seconds here. And what's happened in the background, and I'm going to show you exactly what's happened. So I'm going to create a user, generate and save password. Yep, great. And I'm going to hit next. I have a cluster up and running, and I have, I have a complete set of connection strings. I can use a general connection string, parameters. I can use the Cockroach DB client, all these things. Basically what I have is I have a Postgres cluster. I have a Postgres instance. Basically, it's a Cockroach DB serverless instance. We're wire compatible with Postgres. So any of those kind of Postgres tools you would use or drivers, they should just be able to connect to this. And so you're just going to use the connection string or parameters. I use parameters when I'm using a bunch of different tools, or just use the Cockroach DB client. And now you have a complete relational database that is resilient. It's going to do auto scale, and I'm going to show you what it does underneath the cover. So quick demo basically is it's pretty easy to get basically a Cockroach DB cluster up and running. There's lots of more information on our website about what Cockroach DB does, how it's different than other things. But ultimately, I think in the simplest form, it's kind of like Postgres, but automate all the scale, eliminate the concept of downtime, online schema changes, upgrades, all that. That's really kind of the big stuff of what it does. So that's the quick little demo. I encourage you all to go out and check out a cluster. It's pretty easy to get going. So, okay, so let's talk about architecture. Let's drive into kind of how we did what we did. And this is really the topic of this. So a database is really comprised of three layers. There's a language, there is a SQL execution layer, and there's storage. Every database really is kind of developed and thought of in this way. And really, ultimately, any one of our applications can be thought about like this, right? Like there's an API with my application. Okay, sir, is it a UI? Is it just some basic, REST API? I don't know. Like that's the language. Like that's how you communicate. It does things and it stores data to disk. Literally, a database is just like every other application. They're a little bit more complex. They're not easy to build. I'll tell you that right now. But they're all kind of like this. Now, in distributed systems, I think there's databases on the right-hand side. We have a distributed database. You have to start thinking a little bit differently because, okay, so the language is still the language, storage is still storage, but actually in storage, am I storing data across multiple different places? Because remember, this is a distributed system. This is no longer a monolith. This isn't like one server. We're using many, 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 right? And so we have distributed storage. We have to think about how we get data to that. That's replication and distribution. Distributed execution becomes very important, right? I can have a single instance of Postgres on distributed storage. Well, I still have a single instance. All my writes have to go through there. I haven't solved the scale problem, right? So how do you distribute that for both reads and writes? Well, in our database, or how do you distribute your execution for, I don't know, whatever you're doing in your application? And starting to think about these concepts is actually pretty important. I think the shift towards distributed systems is where these things are happening. So the divide of where you cut your code apart to actually make something serverless is really between execution and storage. Because if we think about serverless and what we're doing at the storage layer, things need to persist. They cannot be ephemeral. Like they need some sort of a consistent existence, right? And you need to make sure that those things are up and running at all times, right? Whereas at the execution layer, I'm not relying on something that needs to be, it's in that item, right? For us, we're just executing a query. We're going to use storage, right? And so taking away and understanding what's ephemeral versus what needs persistence, that's the divide in your application. So look through your code and figure out what is those lines. Do you need to re-architect things? How is this going to work? For us, we had to kind of re-architect and tease these things apart. Luckily enough, it was pretty modular in our code, so it's fairly straightforward to do that. But that's the trick to really thinking through things that are serverless. I've talked to lots of people building serverless applications. This is the same pattern emerging across the board, and I think it's kind of one of these things. It's fairly simple once you see it. Ephemeral versus persistence, scale ephemeral, scale persistence in a different way. And I think that's the trick, right? So let's get into the storage layer. In the storage layer of what we're doing, it's a little bit different than some other databases, right? Like in Cockroach, and I kind of have to go through kind of how Cockroach works, but hopefully this is valuable to you as well from an architecture point of view, just so what we had to do. Ultimately in Cockroach, all the data is stored in a KV. It uses KV underneath. Now we translate KV to relational, so it's SQL. But ultimately, you don't need to know what's going on in this logical key space. But every table is basically this huge monolithic logical key space. It's all ordered, right? And KV allows us to do some really interesting things. And it's all ordered is the key thing. This lexicographically by key is the trick here. And so what we do is we take all the tables and we convert them to KV. The K being a table name, an index, the key, and then a column name. And then the value is the value for that particular column. So let's just show how that works. Here's a quick table. It's the dogs table. I have an ID, I have name, and I have weight. And I have a bunch of entries. Now, this just looks like this is just a table. This is simple DDL, same thing in Cockroach, relational. If you're familiar with SQL, you get this. And this is what my data looks like. I could select all from dogs. This is what I'm going to get back. Underneath the covers, what we do is when we actually store the data at disk, we're going to take and we're going to translate each row into these KV pairs. So, okay, here's the table name is dog. My primary key is 34 for that, the ID, right? And then for the name column, I'm going to have Carl. Okay, for the weight column, I'm going to have 10.1. And I just go down the line. And so we're translating records into KV. Now, if you look at the ordering of this, right? Dog 34, name, weight, dog 78, name, weight, dog 94. So we're ordering them. So this basically all gets encoded. It doesn't look like this dog /34 last name. We're actually encoding these things so that we can actually get really, really, efficient sorts. So underneath the covers, and we know exactly where to insert things into this ordered lexicographic pair. Now that's pretty cool. It's what allows us to actually understand, where tables are when we start to actually move them around. Excuse me, I got a frog in my throat. Excuse me, everybody. Sorry about that. So what did we do to make this serverless? Well, if we're going to use shared storage underneath, what if everybody had a dog table? I wouldn't know which dog table belonged to which person. So what we did is we just basically added a tenant ID to the key. And so now this is Andy K's dog table. So what was my cluster? I forget. It was like, I don't know, Sparkly Kitten or something. I forget. We come up with these funny names, but like that would be, it belonged to that particular tenant. And so what we do is we're just appending that to the front of that. And so now in this huge lexicographically ordered KV set, all of the records for that particular tenant are together. And then inside there, the tables are all kind of sorted, and then the keys and all the stuff, right? So basically what we're doing is we have a complete understanding across everything, and we're using one big shared storage layer, but the tenant key is what's allowing us to understand which parts of this data belong to who, okay? Let's see here. There was a question that came through. What is the most appropriate naming convention to label nodes on a Kubernetes cluster? For instance, controller and responder. Well, gosh, I don't know, Emra. I'm not, that is an interesting question. I don't know. I'm sorry, I'm gonna have to, I don't know the answer to that. Sorry about that. I wish I did. I don't, like y'all, I live in this architecture of the application layer. I don't get too deep into like I understand how Kubernetes works, but managing it is complex, and kudos to all you who do that. But maybe somebody else knows. Sorry, Emma. All right, so that's great. We just talked about the storage layer. We had to actually think about what we were doing from a storage layer. We then had to think about, okay, distributed execution. We're already doing that, but how do we tie that to a particular tenant? How do I make sure that, Jim's execution is just mine, right? And this sort of stuff, right? So again, let's go back to what we're doing in Cockroach, and with this big, huge key space, and we added, we added this whole like the tenant to each of the keys and this sort of thing. And then basically what we're doing is we take this big, huge KV range, right? Or this big, huge KV sort, and we cut it down into these ranges, which is basically these 512 megabit ranges. And think of this as like the way that we shard a table. We're just taking these ranges, and they're small enough that we can move them around really quickly, and we can write them to different physical nodes or different nodes that are running in pods in a Kubernetes cluster, right? And basically that's how we kind of distribute the data. And that's a kind of a key concept in Cockroach. Now, if you're going to do this, we actually have an index, so we can have to find these ranges, so the first range lives on these servers and whatnot. And so we have an index structure that allows us to locate these things. It's very much like a B tree, if you're familiar with what that is. If you want to check out how we do this, our code is completely open. You can go check out our Git repo and actually check this out. Underneath the covers, though, we're using something called Raft. I hope many people on this are familiar with Raft. If you're not, Raft is a really interesting concept as a developer, and anybody who's kind of thinking microservices and distributed systems. If you're on this webinar thinking Kubernetes, definitely kind of check out Raft and see how it applies to what you're doing. But Raft is a distributed consensus algorithm. Now there's another one called Paxos. Some people use that as well. And what it does is it's distributed system, and it's gaining consensus. It really allows us to get atomic writes and consistent reads in what we're doing. Now, what is Raft? Raft is basically, it's an algorithm that manages replicas of whatever it is you want to actually manage and write, say, to disk. In our case, the reason I had this little like blue thing, well, this is that range that I had before. This is the second range. So we basically break up our ranges and then manage them using Raft. Now we create replicas of these. So we have 3 copies here. Within Raft, you want 3 or 5 or 7 or 9, 11, the odd numbers, because you want quorum. So when I write to a Raft group, I want 2 of 3 of these to commit. I want 2 of 3 to say we're good, and then say everything's good, because a third will come along, or 3 of 5, right? So it's a quorum-based transaction, right? So we get this quorum and actually make all these things work. Also in Raft, there's this concept of a leader. It's a special replica, and there's 2 followers. All the writes, all the commands kind of go through the Raft leader to the followers. And it basically manages to make sure everything's good, so that you only have to ask one Raft leader. It's like, great, is this good? Yes, it's good. And I could acknowledge back to the application, whatever it's doing. It's going to have this kind of authoritative, up-to-date answer for what's going on within that Raft group, right? This also allows us to get atomic replication. So we're going to make sure that this is going to happen. Like the whole transaction is going to happen or not. It's going to coordinate with other Raft groups, because I'm doing transactions across, maybe hundreds of ranges, because maybe I'm inserting 10 records, or I'm doing a select across different things and doing joins. Like we can do this kind of cross shard transactions as well. And that RAF leader is going to manage that. It's going to help with consistency and make sure that, you know, the atomicity in ACID actually gets committed. Okay, so if you want to learn more about distributed consensus, you want to learn more about Raft, there is this really wonderful website. I haven't been there in a while. I'm pretty sure it's still going on. Somebody probably would have told me, but the secretlivesofdata.com, I'd go check that out. They give a great kind of visual representation for how Raft works, much better than I could ever do. So we use Raft then to actually distribute data, right? So each Raft group, right? There's 3 of the copies. It's the same data. It's that range. We're going to distribute them across 3 different nodes in a system in CockroachDB, right? And so that's what we're doing. We take the first range, we write it. We take the second range, we write it. We take the third range. What this allows for is kind of scale. I can scale. I can add more nodes, so I get more capacity. All of these nodes could service reads and writes. I'm highly resilient. If I lose a node, I still have 2 of 3 of the copies left, right? And so that's kind of the special nature of what we're doing. And that's helping us at the storage layer. Okay, great. So how do I kind of pull all this together and now make this serverless? And this is the trick of how you use Kubernetes to actually do all this, okay? But one second before I get there, there was a question. Debanju writes, is it possible to allocate a network volume as persistent storage to these nodes? Cluster, on-prem, OpenShift cluster, and network volume EBS, S3, or EFS? Yes, you're going to have persistent storage, and you're going to use basically in Kubernetes, if I presume this is a question, you're going to use the storage class and you'll just make a PV claim from inside that pod. And then you'll use stateful sets within the context of the storage nodes, like where you need to persist. You use stateful sets to actually maintain that persistent connection between that pod and whichever volume you have actually connected to. And then so each of the storage, like here within this context of this is us deploying a database. This could be any application on a Kubernetes cluster. What you're seeing in the bottom, that color is this is just a pod, and this blue box is the application itself. They're all communicating to each other. And so if I wanted storage, I'm just going to take I'm going to use storage class PV claim. I'm going to use, stateful sets to actually attach that to each one of these pods so that I can actually persist that, Demanchu. So it's a great question. It took me a while to figure out the storage class when I got first introduced to Kubernetes, how this works. So for us, this is one single logical database across multiple different pods. Every one of these things can take reads and writes. This is just SQL. You can do cross shard queries. We can actually deploy this across multiple regions and multiple Kubernetes clusters. We can have one single logical database, which is pretty cool, right? So you can, like, your failure domain can actually go up to entire Kubernetes clusters. This was a database that was built literally on the same exact principles as Kubernetes. This wasn't like take a database and do auto sharding and try to make it work in this context. No, this was basically built with the same kind of principles. And that's why it works really well within this context. And using Kubernetes to actually build this out as a serverless cluster is pretty cool. And so what we did is we said, hey, let's look at our stack, our layers within our product. And we basically took this kind of the execution and how to find the data and the language, and we put that in one version. And then we took the other side, and it was the storage of that data, and that's separate. And so what we're doing is we're running a completely separate cluster of CockroachDB that's doing storage only. And each of those kind of pods on the bottom, they have their own PV claim. They actually understand where that storage is. And I'm just communicating to them. They can service requests for basically getting data. And remember, this data is spread across all my users, across all their tables, is now distributed across, okay, this is just 3 nodes running in 3 pods, but it could be hundreds of pods. And the SQL execution layer just works with the storage layer to basically find that data. So lots of different data and users in the bottom, and then the SQL, the execution at the top. And the SQL execution part is ephemeral. So here's a virtual cluster for a particular tenant. We have 3 execution pods, and it's just accessing its data underneath. And I can scale basically the execution now, get really, really efficient, right? So, tenant 1 needs 3 different execution pods because of their bandwidth, right? Tenant 2 only needs, 1. Tenant 3 needs 3, right? And it really depends on on the load that person has. And that's a key concept in with serverless, right? Scale up, scale down, scale to zero, right? Make it really efficient. So, what do I get charged for? Well, for us, it's how much storage and how much compute you use, right? How many transactions. And that's really we're able to scale these things separately, which is a key kind of concept within serverless as we think through these. So how does this look? In Cockroach DB serverless, we have like this storage and replication nodes. We have more than one in each of AZ, but we're doing a lot of them. We're actually working on making this, across multiple regions. So you'll have this across multiple AZs and then regions as well. As beta right now, it's within a single region. You spin up so tenant one is living on, 3 different availability zones. So if I lose an availability zone, I still have two other pods to actually go against. Again, it kind of improves that resilient nature. So tenant 2 comes in as 1, and then tenant 3. And so we're just basically randomly, deploying them across different AZs. Now, if you're going to do this, you need to be able to find what it is your compute layer, right? Where is this thing? And so, we built a piece of software, which is basically a proxy, which understands where my tenant is. So if I come and ask any one of these proxies that are in any one of these AZs running, it knows, it has a manifest, basically. It says, hey, tenant 1, here's where you can find tenant 1's execution layer, and route that query or route that request, whatever you're doing in an application, to that particular user, right? So we tease out the ephemeral compute from the persistent storage, and then you need to find things, and we built a proxy to do that. Really as simple as that, to actually build out, a serverless thing. Now, data also scales, transactions scale as well. So volume of data will scale at the persistent layer down here in storage or replication. We're just going to keep adding capacity there, right? But the ephemeral compute, that goes up and down based on the traffic, right? And so we needed to accommodate elastic usage, deal with spikes, and spin things down to 0. And this is all done via these kind of ephemeral kind of SQL pods. So we built this capability in autoscaler. And autoscaler basically is looking at each particular CPU for these pods and understanding what the usage is over the last 5 minutes. We're looking at peak CPU usage, and all within the context of a particular tenant, right? And so if a tenant needs capacity, we spin up new capacity. If they are not using it, we spin it down. If it falls to 0, we'll completely remove the tenant from the cluster. And so that we aren't using compute that we don't need to pay for. So how does this look for? So here's our diagram from before. We've teased out the 2 layers. Tenant 1, my capacity, my steady state capacity is average here up on the left-hand side. It requires 3 ephemeral pods to deal with that amount of traffic. But at some point I get a spike. I don't know, it's like 5 p.m. and a bunch of people come online, and I'm getting a lot of orders come in, and it's going up. And so what we do is we have these things we have in each cluster, and there's a cluster in each availability zone. We basically have these unassigned hot pods. They're basically instances of my ephemeral compute layer that are just unassigned. So the proxy they just know they're there, but they aren't assigned to a tenant. And so what I do is I basically take one of these hot pods in the proxy, in the manifest, that it says, hey, assign this to tenant 1 and start using it. I have just scaled capacity like that. Because these things are already up and running, it's up really fast. I don't have to worry about the time it takes for the pod to start and then start the application, all these things. It's just running and unassigned. And that's what we did. Now, when things return back to steady state, I spin that thing down. And if it goes all the way, right, it's like middle of the night, nobody's asking for any transactions, we scale that all the way down. So the auto scaler is actually doing this in the background. But then most importantly, say a query comes in, it wakes up that tenant. And so we're able to spin up a SQL pod very quickly. It's under a half a second, and it's for that first query that comes in. I know we're trying to drive that down to under 100 milliseconds, under a tenth of a second. And so, right now that's kind of, a big focus, right? How do we get these up and running really fast? Another big problem you have to deal with in the serverless world, because, well, people want these things to actually come up really quick. And so what we're doing is, again, we just take this hot pod. We don't have that latency of spinning up the Kubernetes, the pod instance, and we're assigning that to a particular tenant. The proxy now understands that. All the proxies know where to go. So if a query comes in against any one of them, it knows where to go get that tenant, right? And so that's basically how it works. So that's what we've done to basically take something what was a distributed system, fairly elegant, but then tease out this kind of ephemeral compute side from this persistent storage layer to make our application serverless. Now, it was fairly straightforward for us because, well, we were already a distributed system, so like kind of applying these principles were a little bit easier. But I think if you start from scratch, thinking about this, like as you build your next application, how do you kind of tease these two things apart? And in the architecture of your application makes a whole lot of sense because you kind of prepare yourself to apply the serverless principles to whatever it is that you're building. And I think that's the trick. And for me, the big takeaway. Again, you saw me create an instance. Y'all please feel free to go out and build your own cluster. It's pretty easy to sign up. We're going to give you a free cluster up to 5 gigabytes of storage a month, 250 million request units, which is pretty ample. A request unit is just basically an abstraction of a query. All queries are not similar, like select star from where and, join blah, blah, blah. That's much more query than select star from customer, right? So that's the way we do that. And it's free. So you can go out and do that right now. Request units are interesting. If you run out of request units, you don't run down to 0. So you have no capacity. We actually reserve enough capacity so that you have enough for the rest of the month. So we basically kind of throttle it. So like this last scenario is easy. You have 8.64 million request units. If you use everything on your first day, you have that amount for the rest of the month, right? So it's fairly good from that point of view. So the amount choose. What's the chargeback model for this Cockroach DB? The charge model is basically you can add a gigabyte of storage or 250 million request units for additional. I think it's $1 per, or I forget what it is. You have to go to the website and look at that, but it outlines all of that. But it's free up to that certain level. So. Okay, so that is all my presentation. There weren't a whole lot of questions. I hope it was valuable to everybody. I do hope to see people live. I'm super excited to go to KubeCon and be live with people in a couple weeks. I'm also really excited to go to Valencia. I would be lying if I didn't say that. The Cockroach Labs team will be there. We'll have lots of engineers who can talk through these things with you. We can talk about our database as much as you want as well. We'll be giving away things, all these things. If you're thinking about going, I really look forward to seeing people again live at KubeCon. It's my favorite 2 shows of the year are KubeCon Europe and KubeCon North America. So I'm really looking forward to getting back with everybody. So with that, if there's no other questions, I wanted to thank everybody for taking the time today. I hope this was valuable to you. I hope I did a little bit of a balance between us talking about a database, but kind of how we thought about going through this serverless journey. I really hope I really hope that was of value to people. So, all right. Well, thank you, everybody. I really, really appreciate it. Oh, that was my other presenter this morning. That's my friend Rain. Oops, I didn't fix this slide. So thank you, everybody. I really, really appreciate it, and have a great day.
Great. Thank you so much to Jim for his time today, and thank you to all the participants who joined us. As a reminder, this recording will be on the Linux Foundation YouTube page later today. We hope you're able to join us for future webinars. Have a wonderful day.